We're now going to work an example problem involving an ideal vapor compression refrigeration cycle, and it will be using R134 as the working fluid. So what I'll do beginning is write out the question. So there's our problem statement. What we have is a vapor compression refrigeration cycle, and it is using R134A. Oh, there should be an L there. I apologize. It's an ideal vapor compression refrigeration cycle. 300 kilojoules per minute. We'll have to convert that into kilojoules per second. We're told the pressure at which it enters is a saturated vapor into the compressor. It's 140 kPa, goes up to 800 kPa, so that's the pressure difference through the compression process. They want us to put this on a TS diagram. They want us to determine quality of the refrigerant at the end of the throttling process. So that would be state 4. And they want the coefficient of performance and the power input or the work into the compressor. So let's move ahead, and what I'll do is I'll begin by writing out what we know and what we're looking for, and then we'll write out a TS diagram and then solve the problem. So those are the things that have been given and what we're looking for. Next step, what we'll do is we'll write out a TS diagram, and then we'll start looking up the property data out of the back of the book using the tables for R134A. So that's our TS diagram, writing out state information and looking at property data in the back of the book. Now you notice when I went in and got the information for state 1, I pulled out the enthalpy. We're at the saturated vapor line, but I also pulled out the entropy because I know that the process going from 1 to 2 is isentropic, and consequently we need to know the entropy at state 2 in order to specify it. That's why I pulled out the entropy. So that is state 2 specified. In order to determine state 3, we go all the way over to the saturated liquid line, and we know the pressure is 0.8 MPa, so that's a pretty straightforward one. So that specifies state 3. Now to determine state 4, remember the throttling process, we characterize that as being a process of constant enthalpy. And consequently, what we can do is say H3 equals H4. We know that we're in the two-phase region at 140 kPa or 0.14 MPa. And so from that, we can determine the quality and determine X4. So there we have all of our states, we have all the information. This is actually the answer to the first part. We can now go ahead and use the values of enthalpy, applying the first law for each of the different components, and determine everything that we need to determine. Now for the coefficient of performance, we have heat transfer from low and work in the compressor. So to determine heat transfer in at low, that's just going to be the difference in enthalpy between state 1 and state 4. And the work in is going to be the difference between enthalpy at state 2 and state 1. The last thing they told us to look for is the work in to the compressor. And that would be the expression for the work in. In order to get that, we need to know the mass flow rate. The way that we determine the mass flow rate is knowing the information about the load, or the amount of thermal energy that we're absorbing in our cold part of the cycle. And from that we can get work in as being 1.26 kilowatts. So the answers to the problem, X4, we have the coefficient of performance, and finally the work into the compressor. And so that completes the example problem as well as concluding this lecture. Thank you very much.